Positioners and dynamic performance. Why positioners matter more than most engineers think. Positioners are often treated as optional accessories, added late, tuned casually, and blamed unfairly when loops misbehave. In reality, the positioner is the dynamic interpreter between the controller's intent and the valve's mechanical reality. If the actuator is the muscle, the positioner is the nervous system. Ignore it, and even a perfectly sized valve actuator pair becomes unpredictable. Purpose of positioners. Image: a positioner's fundamental job is simple in concept and profound in impact. Ensure valve position accurately follows controller output, quickly, repeatably, and independently of disturbances. Accuracy versus responsiveness. Accuracy and responsiveness are related, but not identical. Accuracy: how closely actual valve position matches demanded position, dominated by calibration, feedback mechanism, and friction, determines steady-state control error. Responsiveness: how fast the valve reaches the demanded position, dominated by air capacity, internal gain, and damping, determines dynamic control quality. A valve can be accurate but slow, or fast but inaccurate. Good control requires both simultaneously. Static gain versus dynamic gain. This distinction is where many engineers lose clarity. Static gain, relationship between input signal and final valve position, governs steady-state accuracy, important for repeatability and offset reduction. Dynamic gain, how aggressively the positioner responds to change, governs overshoot, oscillation, and settling time, critical for fast loops and disturbance rejection. A positioner with excessive dynamic gain will amplify noise and induce oscillations. One with insufficient gain will make the valve sluggish and unresponsive. The correct balance is process-dependent, not universal. Positioner technologies image. Pneumatic positioners. Purely pneumatic positioners operate using force balance principles. Characteristics: mechanical feedback via cams or levers, no electronics, rugged and intrinsically safe, limited tuning flexibility. Strengths: reliable in harsh environments, simple troubleshooting, immune to electrical noise. Limitations: limited dynamic adjustment, lower resolution, manual calibration required. They perform well in steady, slow processes, but struggle in modern high-performance control environments. Electro-pneumatic positioners. These positioners convert electrical signals into pneumatic control action. Characteristics: electrical input, pneumatic output, improved accuracy over purely pneumatic designs, moderate tuning capability. Strengths: compatible with electronic controllers, better response consistency, widely used in conventional plants. Limitations: still limited in adaptive behavior, calibration drift over time, minimal diagnostics. They represent a transitional technology between mechanical and fully digital systems. Digital smart positioners. Digital positioners fundamentally change how valves behave in loops. Characteristics: microprocessor-based control, continuous position feedback, adaptive control algorithms, embedded diagnostics. Strengths: high resolution and repeatability, adjustable dynamic response, automatic calibration, friction compensation, valve health monitoring. From a control perspective, smart positioners linearize valve behavior, reduce deadband, and stabilize loops that would otherwise be uncontrollable. Their biggest risk is not misuse, but underuse. Deadband, resolution, and response time image. These three parameters define whether a valve feels alive or sticky to the controller. Sources of friction. Friction is the silent enemy of control. Primary sources: packing compression, stem misalignment, seal drag, bearing wear, surface roughness. Friction causes: deadband, no response to small signal changes, stick slip motion, limit cycles that look like tuning problems but are not. Positioners mitigate friction by applying corrective force quickly, but cannot eliminate it entirely. Shaft windup and backlash. In rotary valves especially, mechanical elasticity matters. Shaft windup, torsional deflection under load, causes delayed motion, introduces phase lag. Backlash, lost motion due to mechanical clearances, causes asymmetrical response, degrades repeatability. These effects mean that actual flow change may lag position feedback, confusing the controller and degrading loop stability. Why actuator plus positioner must be treated as one system. A positioner cannot be evaluated independently. Key system interactions. Actuator volume affects response time. Supply air pressure limits available acceleration. Valve friction dictates required gain. Process speed defines acceptable dynamics. Treating the positioner, actuator, and valve as separate components leads to over-aggressive tuning, hidden oscillations, poor disturbance rejection. Treating them as a single dynamic system allows predictable response, stable high-gain control, reduced maintenance-driven variability. Positioners are not accessories. They are control amplifiers sitting at the boundary between software intent and physical reality. When positioner dynamics are understood and engineered correctly, valves behave transparently and loops feel effortless. When they are ignored, every control problem looks mysterious and every fix looks temporary. Valve performance and control quality. From datasheet to real-world behavior. This module is where paper specifications meet plant reality. A valve can be perfectly sized, correctly actuated, and equipped with a modern positioner, and still degrade control quality if its performance characteristics are misunderstood. Control engineers do not tune controllers against datasheets. They tune against valve behavior as experienced by the process. This is the final translation layer between design intent and operational truth. Static performance image. Static performance describes how a valve behaves once it has settled, independent of time. These characteristics define the minimum controllable change a loop can achieve. Deadband. Deadband is the range of input signal change that produces no valve movement. Engineering sources: packing friction, seal drag, stem misalignment, mechanical clearances, poor positioner tuning. Control impact. Small controller corrections are ignored. Offset persists even with integral action. Loop exhibits limit cycling around set point. Deadband is especially damaging in temperature control, composition control, tight regulatory loops. A valve with excessive deadband behaves like a controller with a blind spot. Hysteresis. Hysteresis is the difference in valve position for the same input signal depending on direction of travel. Root causes: elastic deformation, frictional memory, backlash, shaft windup. Control impact: asymmetric response to disturbances, inconsistent gain depending on direction, apparent random variability. Hysteresis does not show up clearly in steady operation. It emerges during load reversals, which is exactly when control quality matters most. Sensitivity. Sensitivity defines the smallest change in input signal that produces a measurable change in valve position. Limiting factors: positioner resolution, actuator compliance, signal noise, mechanical friction. Low sensitivity means the controller cannot finely modulate flow, integral action becomes aggressive, noise-driven oscillations increase. High sensitivity without stability, however, leads to chatter. Control quality lies in the balance. Dynamic performance image. Dynamic performance defines how fast and how cleanly a valve responds to change. Response time T63. T63 is the time required for the valve to reach 63% of its final position following a step change in input. Why T63 matters? It represents effective valve bandwidth. It correlates directly with achievable loop speed. It defines how much controller gain can be applied safely. A valve with slow T63 forces conservative tuning even if the process itself is fast. Small signal versus large signal response. Valve dynamics are nonlinear. Small signal response governs disturbance rejection near set point. Large signal response governs startup, shutdown, and upset recovery. Common reality: valves respond sluggishly to small changes due to friction, respond aggressively to large changes once friction is overcome. This mismatch produces limit cycles during steady operation, overshoot during set point changes. Designers who only test full stroke response miss the behavior that dominates daily operation. Why stroking time is misleading. Full stroke time is often specified and often meaningless. Problems with using stroking time: ignores friction thresholds, ignores mid-stroke dynamics, does not represent normal operating range, overemphasizes actuator speed. A valve that strokes fully in 2 seconds may still take several seconds to respond to a 1% change, which is what control actually needs. Impact on loop stability. Image valves are not neutral participants in control loops. They shape loop dynamics continuously. Interaction with controller tuning. Controller tuning assumes predictable gain, minimal deadband, consistent response time. Valve imperfections violate all three. Consequences: overtuned loops oscillate, undertuned loops drift and lag, Retuning treats symptoms, not causes. No tuning method can compensate for poor valve dynamics indefinitely. Valve-induced oscillations. Many oscillations blamed on controllers originate in the valve. Common valve-driven mechanisms: stick-slip motion, gain changes with travel, directional hysteresis, positioner over-amplification. These oscillations persist even with conservative tuning because the root cause is mechanical, not algorithmic. Performance metrics. Engineers should track. To manage valves effectively, engineers must track performance, not just availability. Critical metrics: deadband percentage, hysteresis width, T63 response time, small signal gain, valve travel distribution, time spent near seat or full open. These metrics reveal whether a valve is controlling, merely moving, or actively degrading loop quality. Valve performance is not binary. A valve does not simply work or fail. It exists on a continuum between transparent control element and dominant disturbance source. Engineers who understand and quantify this behavior move beyond firefighting and begin designing loops that remain stable, efficient, and predictable throughout the valve's life.